Thank you for joining us this morning. I'm really excited to be here today co-chairing this session with Christine Wiedinmyer. Today we're going to be talking about satellite-derived air quality products for health studies. I just want to spend a couple minutes right now to kind of set the stage and tell you about the path that brought us here. So I joined the HEI Research Committee in fall of 2021, and shortly after I joined, I got an email from Allison asking if I would be interested in helping with a workshop to determine whether or not HEI should be doing more in this space of satellite-derived air quality and health. I enthusiastically said yes and was very excited, and so about 4 years ago now, there was a virtual workshop that spanned 4 weeks. And while virtual is rough, the great thing about that was that we were able to bring in speakers from around the world, and hundreds of attendees from all across the globe joined. It was really a fantastic workshop. There were 4 guiding questions, and the aim of the workshop was to understand how to make satellite-based products more accessible, more usable, more understandable, and more reliable for health researchers. Through that workshop and the many conversations after, it became increasingly clear that HEI had a really unique role in this space at the intersection of satellite-derived air quality and health. HEI's experience with large-scale epidemiological studies and burden assessments placed them nicely at this intersection. Satellite products are increasingly used for health effects studies because they offer an opportunity to get data where we previously could not. This was clear in many of the posters here on Sunday, Monday, and I'm sure today after this session as well. For example, one of the Jane Warren awardees, Abhishek Anand, leveraged satellite products to do a health effects study in Ghana. There were also several posters using satellite products in regions where ground-based monitors are limited. So South Asia, there were several health studies looking at air pollution exposure in India that leveraged satellite products. Also in remote regions of North America where the ground-based monitors are limited, people are leveraging these satellite products to get exposure estimates there as well. And then I feel like there's also some very clever use of satellite products to look at flare detections, fire detections, so being able to look at unique sources of air pollution by leveraging these satellite products. Also yesterday, there was a discussion on the importance of quantifying bias and uncertainty. That was a major theme that also emerged from our satellite workshop, and being able to understand uncertainty in these satellite products is really important. There's also new satellite products coming online. So for example, we have almost 2 years of tempo now. So we have geostationary products that now let us go to a sub-daily exposure estimates. Also, new species being able to be quantified, like trace gases, NO2, ozone, and then with Maya, there will be speciated PM2.5 components. So all this to say is it's a very exciting time to be able to use these satellite products in the health effects studies. And so our session today brings 4 experts that work at this intersection of satellite-derived air quality and health, and they'll give us an overview of satellite remote sensing specific to air quality and health applications. So with that, I would like to introduce our first speaker, Tracy Holloway.
Good morning, everyone, and thanks for joining this morning, and thank you to the organizers at the Health Effects Institute for inviting me to participate in this meeting. I am really excited to talk to you today about satellite data for health applications. This is one of my favorite topics. For over 10 years, I've been leading the national team for NASA to make satellite data more relevant to public health and air quality decision-making. And this team is called the Health and Air Quality Applied Sciences Team, which we affectionately call HACAST. And we have a lot of resources available online. So if you want to connect after this meeting or be part of our community, this is a very much open invitation to all of you. So when we're talking about satellite data, what we're really referring to are data products that come from this constellation of instruments up in space, orbiting the Earth and looking down. There are a lot of different instruments aboard a lot of different satellites, and they each have unique characteristics in terms of what they measure and what their spatial and temporal coverage is. Last year, I was asked to lead the annual critical review for the Journal of Air and Waste Management, and this was on the topic of satellite data to support air quality assessment and management. I think these issues are extremely overlapping with the needs of the health community, and much of what I'm going to be pulling from today is from that critical review. So that's another resource as a follow-up from this conversation. But one of the places that I like to start the conversation around satellite data is, what do people already think about it? And there has not been a study in the US about what the health community thinks about air quality. You all have your own perceptions already. But in the UK, a couple of years ago, some colleagues did address this exact question. And they considered two groups, Group A and Group B. And Group A we can think about as scientists or researchers in the satellite space. And the other group we can think of as stakeholders or data users in the health, policy, regulatory space. And they asked a lot of interesting questions, but here I'll say the basic one. Do you consider satellite air quality data in their current state to be useful to potential end users? So you might think about your own answer to this question, and I'll share that the perspectives of these two groups were very, very different. Whereas researchers working on satellite data were enthusiastically saying, yes, the data are useful, the actual end users who might use it were predominantly on the answer of no. And I think this shows that there's a disconnect between the health community, the policy community, the regulatory community, and the capabilities of these satellite data. And this is not a question of they just need to know more. It's actually a question of how can we make the data more useful to the actual information needs of the health community. There are a lot of ways that data products are used for health assessment, but certainly the most common is to supplement or inform the same issues that are currently measured by regulatory monitors. The US is the most monitored country on Earth, but even in the US, only about a quarter of counties have a single monitor. These are two maps showing the distribution of monitors in the United States, EPA regulatory monitors, I should say. This does not include low-cost monitors. The top map shows PM 2.5 monitors. The lower map shows gas phase monitors. And you can see that these really are missing a lot of rural areas. And even in urban areas, there may only be a few monitors available. So I always like to start with just putting it out there. What can satellites do and what can they not do? And they really cannot monitor surface level air quality. They do not detect the same things as monitors. I wouldn't quite say it's apples and oranges, but perhaps apples and pears, because they're similar but not the same. They do not directly measure emissions, the flux of chemicals into the environment. They do not detect all pollutants of interest. They only detect those that can be, that have a signature in terms of how they interact with radiation that can be picked up by satellites. And they do not replace ground monitors, in-stack emissions, or other sort of standard air quality data products. So first, that's the bad news. But the good news is that they detect the column because they're looking down from space. So it's kind of like if you're looking down through a pond. You can see what's in the pond, but you may not be able to tell exactly whether it's at the surface or high up. Some satellites detect layers, so you can detect near surface or upper tropospheric, and they detect a lot of chemicals, especially nitrogen dioxide, aerosols in the atmosphere, formaldehyde, sulfur dioxide, ammonia, carbon monoxide, carbon dioxide. They can track spatial patterns and trends and events, and they can be combined with other data products to estimate surface concentration and human exposure. So there's capabilities, but it's not just plug and play the way you might use monitors in your work already. When we're thinking about satellites up in space, there's two categories that really relate to air quality relevant data products. There are what are called low Earth orbiting or sometimes polar orbiting satellites, that's shown in the blue. And these provide data once a day or sometimes less than once a day, like once every 3 days. These orbit the entire Earth. So the good news is they're giving you global data on a regular frequency, sometimes a snapshot every early afternoon, for example. There are also what are called geostationary satellites, and these orbit further out from Earth, and they orbit with the Earth, scanning across a domain. So these don't give you the whole globe, but they do give you higher time resolution over a particular region. So Heather mentioned the TEMPO satellite that was launched in 2023. That is a geostationary satellite over North America that gives hourly data through the daytime. And that is the first geostationary gas phase instrument over North America. When we think about how to use satellite data, it really is part of this portfolio of data products with ground monitors, aircraft observations during flight campaigns, computer models, really thinking about it as a data ecosystem. And if you haven't looked at satellite data yourself before, I would, just pop this up as an example of what it looks like. It looks very noisy. And what you see, this is for a specific hour over North America from the TEMPO satellite. And one of the biggest limitations of satellite data, other than the column, is that they do not detect data when we have clouds. So when you have clouds, there's no data are available. That's what shows up here in gray. Now, if you average over multiple days, you can compensate for the clouds because it's not usually cloudy in the same place all the time. And that's why when you see data maps that cover everywhere with no clouds, it's usually because they've been averaged over a year or a month or something like that. But even despite the noisy data, we can still get a lot of useful information about individual events. And this, I picked this snapshot over Chicago area, in part because we're all here in Chicago, and I spoke on October 21st at the Air and Waste Management Great Lakes Conference here in Chicago. And at that point, I decided, I'll just take the day before the conference, which was October 20th. I tried to do the same for this conference, but there were two problems. One, the Health Effects Institute is so organized that they ask for my slides a few days in advance. And two, that actually a few days in advance, it had been kind of cloudy over the Chicago area. So I think it sort of illustrates the issue. But the data are very easy to use with this public interface that I have here in the URL. And you can zoom in and go hour by hour, day by day. And what this is showing for this day in October is that you had the plume over Chicago in the morning, but over the course of the day, it is transported up the coast to Wisconsin. And I live in Wisconsin. People in Wisconsin often complain about air pollution from Chicago. And here we have a very clear satellite image showing a plume moving right up the coast. When we average it over longer timescales, we can reduce the impact of clouds, and that gives us information we can compare more directly with monitors and models. And this is a figure from the review paper I mentioned earlier, and also taken from a paper by, one of my colleagues, Gage Kerr. And I think this shows over the Maryland area the pros and cons of these different data products. The monitors, here there's 3 over a fairly small area. That's pretty good, but it still leaves a lot of area with no data. The model is apples to apples in terms of the units, parts per billion, with the monitors. But one, the model may not be totally correct. We can then compare that with satellite. But note the difference in the units. It's molecules per centimeter squared. So it's as if you take a little centimeter on Earth and then count how many molecules all the way up to space. And so we could analyze the model in those same units, but I think it shows how these can be compared with each other. When we're thinking about PM 2.5, this is probably the data product where we are the furthest along in terms of estimating surface concentrations. And the reason is because we can benefit from advanced methods in data fusion, I see my colleague Yang Lu in the audience, who's a real leader in this area, and where you take satellite data, ground-based measurements, and computer models, and especially with new AI algorithms, fuse them together to come up with an estimate of near-surface PM 2.5. Here's a map over the United States. This is from work by Aaron von Dunkelaar and Randall Martin and their work, which is now based at WashU in St. Louis. I would say this is the most widely used data product available for annual average PM 2.5. And it's used in the annual reports of the Health Effects Institute, of course, and it's available globally. It's renewed every year, and it is publicly available for free. So it's great. Now, a lot of people ask me about the total inventory, like what are all the data products? You showed us tempo, you've showed us some PM 2.5, what are all the data products that are available? And I really don't like this question because there are so many products available that just putting a laundry list is not that helpful. However, I got so many requests for this kind of a list that we did put it in our paper. So I'll show it here. There it is for aerosol optical depth from these daily global satellites. We can do the same for gas phase. We can do the same for geostationary. But I think it isn't that helpful to just have everything in a list. But if you want it, you can refer to the paper. What I think is helpful is to think about which of these products are the most mature, which have been used the most. And toward this end, one of the kind of heuristics that we might look at is which data products have been published. And we looked at papers using satellite data for air quality, and we see that the two most published topics are around PM 2.5 and aerosols. The AOD refers to aerosol optical depth. Coming in second is nitrogen dioxide. Coming in third is methane. So these are really the data products that you hear about the most in the air quality and health community because they're the most mature. I mentioned the HACAS team that I lead. Our website is hacas.org, and I welcome you to be involved in that activity. We have meetings every 6 months. We have a lot of data products that are available, and our approach is to really try to be a front door for the air quality community and the health applications of air quality as a big part of that. One of our program managers, Helena, will be speaking in this panel in a few minutes. One of the things that we've been doing over the years is to try to understand how user communities can benefit from satellite data products, and we found that the voices of these user communities are really an important part of building bridges with new groups. And we established our HACAS ambassadors to help recognize individuals who are really helping get this engagement of these free, publicly available, powerful data sources. And we're really appreciative for Allison and Pallavi's participation from the Health Effects Institute. Zach Edelman is here from LADCO, and this is actually a little bit outdated because we already have 3 new ambassadors not pictured here. The ambassadors at our very first meeting suggested a flow chart because they said, well, maybe we can try to help move from what people need to what data products are available. And I had thought, oh, good idea, this might be a page or two. Well, we put it together, it's now over 100 pages, but it's kind of a choose-your-own-adventure process because if you want data over the United States, you have different options than if you want it over the globe. If you want it for NO2, you have different options than PM 2.5. So we hope that you find that useful. And just to end with a couple specific examples of how satellite data have been used by different health-related organizations, we were really pleased to work with the American Lung Association, who released 2 reports in late 2024 about the possibilities of satellite data. And actually, I've been working on some published papers with the American Lung Association that are coming out this spring. The EPA integrated satellite data into their annual air trends report to look so that you can visualize all the improvements in air quality, but you can also visualize the impact of wildfires and new sources as health risks. And as a third example, I'll note that LADCO used the satellite-derived PM 2.5 from Randall Martin's group at WashU to inform rural pollution levels away from monitors. So these are just a few examples. There's many, many more, as was mentioned from the poster session just yesterday. But I think hopefully this tees up the more in-depth comments from my panelists who are coming next. And if you're interested in kind of the broader work of my team at the University of Wisconsin, I invite you to check it out at hollowaygroup.org. So thank you very much.
Thank you, Tracy, so much. Our next speaker is Carl Mannings from Morgan State University in Goddard. So, Carl.
All right. So thank you for the invitation, and thank you to Tracy for that overview. My objective here is going to be to take from that general overview which Tracy gave and drill down into a little bit more of the specifics of how we get to surface level concentrations from satellite data products, and using that as a case study, that data set from Aaron von Donkelaar and Randall Martin, which Tracy mentioned in her talk, as a main case study, as to examine the methodology and specifically how they thought about uncertainty in that work and how they quantified uncertainty, because I think that's a topic of interest to the panel in this community as well. If there's time, I'll present a little bit more on some other case studies, but I'd like to round off with, in addition to the hate gas community, which Tracy already mentioned, some additional resources for learning more about how these products are developed and how you can use them. So going back to that data product which Tracy mentioned, this is another map from the paper describing that product of the global surface PM2.5 estimate from that data product. As Tracy said, but I'll just reiterate, this is surface level PM2.5 derived from, among other things, the satellite aerosol optical depth. So aerosol optical depth is more or less an optical measurement of the total amount of light blocked by aerosols throughout the atmospheric column, so from the surface up to where the satellite is orbiting. And this is related to, but as Tracy mentioned, it's more of an apples to pears comparison between this optical property and the surface level concentration in terms of the mass of particles of a particular size fraction. So that's generally what the product looks like. And in the paper, they also present the standard deviation, or the uncertainty in that product expressed here as the standard deviation. In the nomenclature of the paper, they call that PM2.5 prime. And if I can manage to sort of toggle back and forth between these two, you can see, first, in general, there's a trend, as you might expect, where higher PM2.5 is associated with higher uncertainty. But there's also areas which go against that trend. So if you look at Greenland, PM2.5 estimate from the product, very low, about 1 microgram per cubic meter for this particular month. But the uncertainty is quite high there. And that's the function of a couple of different factors, specifically for the case of Greenland here. Number one, Greenland is covered by a lot of ice. Ice is a very reflective surface. That reflectivity of the surface interferes with the algorithms used to determine aerosol optical depth from the measurements taken by the satellites. So that was one big source of uncertainty for Greenland in particular. Another big source of uncertainty is we don't have a lot of ground-based monitors in Greenland, especially over those icy and glacier areas. So the combination of uncertainty in the satellite product, uncertainty in the ground-based measurements, leads to high uncertainty in the overall fused product. And for those boxes, the paper sort of cites just general uncertainty ranges for those areas. So in Asia, South and East Asia, they note about 20 to 30% on average uncertainty. North America, 30 to 50%, and Europe is about somewhere in the middle, about 20 to 40%. So what I did here is I tried to kind of put into a schematic what they explained in a lot more detail in the paper about how they came up with this hybrid uncertainty estimate. And basically what they did is they took the maximum of 3 different types of uncertainty, which they tried to quantify in the paper. The first type of uncertainty they look at is uncertainty in the aerosol optical depth. So this is uncertainty in the satellite data. And this can come from a variety of sources. They're using a combined data from multiple satellite instruments. These instruments can have variability and biases with respect to each other, so that's one source of uncertainty. The instruments themselves have noise in their measurements. That's another source of uncertainty. There can be systematic biases in the measurement, as Tracy illustrated. When there's cloud cover, there's an inability to retrieve this aerosol optical property. So that can be a source of a systematic bias in terms of the missingness of the data in particular regions due to cloud cover, for example. Different types of aerosols have different optical properties. That's another source of uncertainty. And as I mentioned for the case of Greenland, there's the surface reflectance. So that's another source of uncertainty. Overall, the way they characterize those uncertainties in this particular paper is they look at comparisons against AeroNet. So AeroNet is a network operated by NASA of ground-based sun photometers, basically instruments on the ground at various locations around the world, which look up at the sun and calculate aerosol optical depth based on those measurements. So this is a similar but an independent data set from the satellites, which are looking down, and it's subject to its own uncertainties, but it's treated by the community as a sort of the gold standard reference for aerosol optical depth, for example, because you don't have to deal with things like surface reflectance if you're looking up from the surface at the sun directly. So they use this AeroNet data to estimate the biases, the variability, and the variance across all the aerosol optical depth data products they used. And they use that to characterize the uncertainty in the aerosol optical depth itself. Second big source of uncertainty is due to what they call the geophysical relationship. Basically, what is the relationship between the aerosol optical depth, which is a column quantity, and the surface level PM2.5. And in this paper, they're making use of a global atmospheric chemistry and transport model called GeoSChem to characterize that relationship. And there's all sorts of uncertainties associated with the use of that model. For example, the model is operating at a specific spatio-temporal scale, which is maybe not representing certain very local processes. That's one source of uncertainty. This model needs to be driven by meteorology. That's a source of uncertainty. The model needs to take into account the surface topography, and the exact way that's done is potentially a source of uncertainty. The model is capturing different chemical mechanisms, but it may not capture all chemical mechanisms that might be relevant in all cases, or there may be slight inaccuracies in how those mechanisms are captured. That's a source. And then, of course, with any kind of model approach, you need to provide the emissions, so what's actually being put into the atmosphere, and that is a major source of uncertainty with any modeling effort. So the way they characterize this, again, in the paper is more or less through a cross-validation with in situ data. Obviously, they go into much more detail in the paper about this, but just very briefly, they take their sort of first estimate of PM2.5 from their method. They compare that against the ground monitors wherever they are in the world, the data set, in terms of the data set that they're using. They calculate the residuals, the difference between those two, and they try to regress those residuals against various covariates which are related to these sources of uncertainty that they identify and try to capture it in that way. And through a cross-validation effort, they're able to get a range of different parameters associated with those covariants, and that gives them a range of uncertainties in this geophysical relationship. And finally, the last piece they consider is more or less just taking into account some physical limits, like limits of detection of instruments, for example. And that's basically to just give a lower bound to the uncertainty in certain cases where they really don't believe they could be more accurate than, for example, the limits of detection of certain instruments. So how does this work in practice? This is some figures I pulled from that paper. The two plots on the left are assessments of the hybrid PM2.5, that's their estimate on the vertical axis compared to the surface observations on the horizontal axes for January 2018 on the left, July 2018 on the right. And the statistics in the lower right corner of those plots are results of their cross-validation studies, so that you can see the types of statistics. Obviously, there's a lot more detail in the paper. Another thing I want to highlight is their characterization of the quality of their uncertainty estimates. I pulled some numbers out of the paper just to illustrate this, but for example, for January, through a cross-validation, their estimated uncertainty through their model approach was 1.9 micrograms per cubic meter in this particular test, compared to the actual differences with the ground observations was 2.2. So it was, I would say, from that assessment at least, a pretty credible estimate of uncertainty in their approach. And obviously, if you want to learn more, you can read the paper and dig into details for different regions. These obviously will vary region by region, and they have maps of how this worked out in different regions. I did also want to add, this is some of my own work I was involved with at least. It's a little bit more of anecdotal, but it might be interesting to this group. So in this study, I compared on the vertical axis, those are the estimated PM2.5 from this data set, which I've just been talking about. And on the horizontal axis, this was ground-based filter samples, which some colleagues collected in a couple sites across rural Uganda. The error bars, so the vertical error bars of those scatter plot, the vertical error bars are the plus or minus 1 standard deviation from the uncertainty estimates produced by the methodology. So that's sort of the stated uncertainty in the methodology. Horizontal error bars are due to the fact that these monthly averages were computed based on filter samples taken at selected days during the month. So based on that, there's some statistical uncertainty in what the monthly average might be. So a couple things to note. First off, I think the fact that the order of magnitude of those uncertainties is roughly similar for both the satellite-derived and this ground-based measurement, at least the technique they were using, the sampling approach they were using. There tend to be a similar order of magnitude for most of these samples, so that's maybe an interesting result. Also, that dashed line there's the one-to-one line. You can see that most of these measurements are probably within 2 standard deviations of that one-to-one line. So there's some uncertainty there, but it's not completely unreasonable, the estimates of uncertainty that are being given. In this particular case, we noted about a positive bias of about 9 micrograms per cubic meter across all these, with some variability around that. And that's just to note and to keep in mind that these uncertainties should not be treated as independent, especially if you're looking at a very small region, as we did here. If the estimate is off by a certain amount for one location in a certain month, there's going to be a high probability that nearby locations for the same time period will have a similar tendency in the error. So it would be, I think, not correct to assume independence in the errors, and to think a little bit more about how error correlation might be considered. For the sake of time, I won't discuss this in a lot of detail. This is another methodology, as Tracy mentioned, using machine learning. In this case, going from a global model to point-specific estimates using a machine learning method calibrated to data at each location. But what I wanted to really illustrate with this case is they're looking at evaluations in a couple different ways for different purposes. So on the left is a figure illustrating some of the standard performance metrics you might see: correlation, root mean square error, and so forth, bias for each location. But on the right is a confusion matrix, basically, of the air quality index that was predicted by their forecast model compared to the actual air quality index. And this is really tailored to the intended use case of their data set, which was to inform air quality forecasting at specific locations. So this is an assessment of uncertainty or of accuracy, which is really tailored to that specific application. So just to kind of illustrate that and put out a plug for really thinking about how to tailor assessments of uncertainty to the specific purpose for which the data set is intended to be used. And I think that was a useful example that they gave in this paper. I'll skip that for the sake of time and just finish off with 2 additional data sources in addition to HACAST, which was already mentioned. The NASA Applied Remote Sensing Training Program, or RSET, is NASA's effort to provide capacity building to help people use NASA satellite and satellite-derived data for various applications, including health and air quality. So we have freely available trainings on a variety of topics. I will say that we are in the process of developing a training focused on those PM2.5 products, which I was just talking about. So hopefully that will be coming out in July. If you look at the website and the QR code, that'll be announced there, hopefully not too long from now. Second resource, the Group on Earth Observations has their health community of practice. This is various groups dedicated to advancing the use of Earth observations for health applications. In particular, myself and Nathan Pavlovic lead the air quality working group within that community of practice. We host monthly meetings where we try to talk about some of the latest developments and how various types of Earth observation data are being used for health applications around the world. So if that's of interest, you can reach out to myself or Nathan to sign up for that group. So I think we're taking questions at the end, but thank you very much for your time.
Thank you.
For that one.
Thank you, Carl. Yeah, there will be a panel discussion at the end, so you'll get a chance to ask speakers questions. Our next speaker is joining us remotely. I would like to introduce Helena Chapman. Ah, perfect. Thank you. You're on the screen now.
All right. Can you hear me okay?
Yes, we can hear you.
All right, perfect. Well, it's an honor to be here with you virtually. Thank you so much for the invitation to really share a little bit about our NASA Earth Action Program. So here we can see, as Tracy and Carl very articulately mentioned, the beauty of using Earth observations for multiple applications related to health and air quality. And yes, that is near and dear to our heart, but in our NASA Earth Action Program, there are many other applications for some of these Earth observations as we use for both natural and anthropogenic changes to our ecosystems. And with that, we use Earth Action to really connect multiple levels. And these are just some of many that we use. Earth observations to be able to help us drive U.S. economic growth, turning some of those data into real-world solutions at the practical level, being able to harness some of the new technologies that we have, including artificial intelligence, to be able to accelerate some of the work that we're doing. Being able to provide that information, as NASA is an R&D agency, being able to provide that broker of that information, be able to provide that to some of our local leaders so that they can have the appropriate information relevant to their work so that they can continue to make substantial action. And obviously being able to strengthen and reinforce some of our resilience across the country, in particular with some of the extreme weather effects that we're observing. So as we see that within our health and air quality applications program, we promote the use of Earth observation data in an array of public health applications, including air quality to environmental health and infectious disease, in particular to protect and enhance health security in the economy. This is not, we use the One Health framework, or that interconnectedness between humans, animals, and the environment to be able to serve as that framework for the work that we do and our program funding. But this work, as mentioned in the previous presentations, is not done as an individual person. It is done in groups and often across different sectors. And that's really forefront for the One Health framework. And here we can see many, but not all of the agencies and partners with whom NASA and NASA-funded researchers have collaborated. So across public-private sectors, local, state, international partners. So to give kind of a view of two examples that are different from what has been previously mentioned that are related to air quality, I'd like to present these two that are actually have been part of a platform, the NOAA platform, and this is actually part of the Caribbean Coastal Ocean Observing System. So in this case, we'll look at Sahara dust. So again, something that is not only a natural phenomenon coming from the Saharan desert across the Atlantic Ocean, providing nutrients to coral, to land, but also impacting air quality. And Dr. Mendez-Lazar from the University of Puerto Rico was interested in developing a decision support tool to monitor these aerosols that could help guide some of the policy decisions as well as some of the public health messaging for dust storms. And if we can see on the left, there are two images that were taken right in June 2020, just as this decision support tool had its beta operational platform. We can see the satellite image of SOMI MPP VIIRS looking at, again, that AOD, that dust concentration in red, as we're seeing it just go across the Caribbean basin, advecting westward. And this was an opportunity to be able to showcase, again, something that you can go right now using the QR code to the characterize platform. And you can see that not only can you see wind, ocean currents, and sargassum on this platform, but now there's an aerosol monitoring tool added, and both in English and Spanish. Another opportunity, again, looking at this coastal ocean observing system, is also related to the Gulf, the Gulf of Mexico, of America. And we see this, we can look at the NOAA team was interested in being able to expand beyond the current forecasting, respiratory forecasting measures, in particular for the dinoflagellate Carenia brevis, which, when it's accumulated, can have these aerosolized toxins, and those toxins can impact respiratory health, especially those who are living or working on the coastal communities. So this team, again, took different types of environmental observations, but in particular used something called a HAB scope. So some citizen science applications where they trained students all the way to retired scientists with a filter and asked them to take some photos and videos of the water in this area that could then be verified and counted. The Carenia brevis cells could be counted by the NOAA scientists to determine the accumulation of that presence and extent of these algal blooms in the Florida Gulf Coast. This app of the citizen science opportunity offered some validation to some of the satellite data, including, as we know, on our coastal communities, there's a lot of opportunity for on-the-ground data collection. And if you go to the QR code, you can actually see, this is what I just took right now, we can see the algal blooms, and actually since this project ended with NASA funding, the project has continued to extend with additional funding through the other areas on the Florida Gulf Coast. So a couple opportunities moving forward that some have been mentioned already, but just to highlight, if you would like to get involved and learn a little bit more, stay tuned and buckle your seatbelts. There's going to be a lot moving forward, especially revolutionizing how we look at air quality, both from an earth scientist perspective, but also as a health scientist perspective. So Maya, as was mentioned, is the first time that there's going to be collaborations with epidemiologists and trained in epidemiology and medicine. This is fascinating to me to be able to not only to understand, well, PM is dangerous for health, but actually look even deeper at some of the mixtures of particles with different sizes, shapes, and compositions to be able to better understand these health impacts. And also, if you'd like to go down a large rabbit hole, highly encourage the Interagency Supported Earth Information Center. There are currently 9 themes, including air quality, and you can look at earth.gov. This is the hybrid exhibit. The in-person exhibit is actually at the Smithsonian Museum of Natural History. And as Carl articulately mentioned, the GeoHealth community practice is a great way, including the air quality, but also think about some of your cross-cutting themes. If you're working in air quality, you may be interested in looking at the impacts on heat or in healthcare infrastructure. This is a great opportunity to leverage your expertise and expand your networking. Because we all, after all, are one health change agents in our own disciplines, whether we come from the earth science discipline, whether we come from the health disciplines, there's a great opportunity to be able to help translate the information that we know that's dear to our heart, the bread and butter we have on a daily basis, and be able to help continue to foster some of the connections and engagement and be able to leverage the expertise and scientific knowledge sharing. Thank you for this opportunity to share a little blurb about what we do in the NASA Health and Air Quality Applications Program. Thanks.
Thank you so much, Lena. And thank you for joining us online today. Our other speaker today is Ellen Considine from University of Colorado, so I welcome you up.
All right, looks like tech is working. Great. Hi, everyone, and thanks so much, HEI, for having me. It's been a great conference so far. I will just dive right in the interest of time. So I was asked to provide a high-level overview of methods for uncertainty quantification, but coming from the statistical and machine learning perspective, my training's in biostatistics. So this is to complement the things that Carl was saying about more of the uncertainty coming from the satellite retrieval. Here I'll focus on the question of, is uncertainty being modeled or estimated internally or after the fact? Are uncertainty estimates being evaluated or calibrated to different conditions of interest? And briefly, what metrics are then available for those of us doing downstream health analyses? For this first piece, if we were interested in modeling uncertainty internally, some ways to do that would include Bayesian statistical models with which we work directly with probability distributions. We can explicitly model spatial structure. We could also think about using machine learning-based approaches, some of which can allow us to predict quantiles instead of just a single point estimate. We could also repeatedly perturb the model parameters to generate a probability distribution of predictions, which is referred to as Monte Carlo dropout. If instead we are going to estimate uncertainty after the fact, this is kind of related to what Carl was mentioning about calculating the residuals, right, comparing monitor observations versus our model predictions. We could think about interpolating or smoothing those over space and time. Or we could think about, fitting the model multiple times, right, on different resampled subsets of our data. This is referred to as bootstrap, unsurprisingly more computationally intensive, right, because we're refitting our model lots of times. In the interest of time, I will briefly state that we typically want to try to model uncertainty internally and then sometimes have a secondary stage of modeling the residuals. Traditionally, some of these Bayesian statistical approaches have been more computationally intensive, but modern adaptations are making these more computationally viable, sometimes also combined with machine learning approaches, kind of different places in the pipeline. Moving over to this question of, okay, we have our model estimates, how do we evaluate these and kind of assess the uncertainty quantification? As Carl also mentioned, we often in environmental sciences have to worry about this issue of spatial and temporal autocorrelation, right? So observations taking it more similar, points in space or time being more similar to one another. We want to account for that when we're doing things like cross-validation to not kind of be overconfident in our predictive ability. Something that folks in the room might be a little less familiar with is this question of calibration of our uncertainty estimates. So if, for instance, we're trying to generate a 95% confidence interval or predictive interval, do our true monitor observations fall within that interval actually 95% of the time? That's what it means to be calibrated. We could also do this for 50%, 80%, whatever. 95% is kind of our standard way of thinking about confidence. And then if our observations don't fall within that interval, the kind of nominal level, often, right, our interval ends up being too narrow. Can we think about scaling, right, increasing the width of that interval? And this type of approach is referred to as conformal prediction. That's kind of a cutting edge area of interest methodologically. And then lastly, you might be more familiar with this in the context of evaluating your model estimates, but we also want to think about kind of evaluating our uncertainty calibration across different conditions of interest, right? Whether that's different regions, land use types, meteorological conditions, pollution concentrations. So increasingly, folks are thinking about calibration across all these different areas as well. And then briefly, for those of us who end up trying to use these air quality estimates later down the line, we want to think about what metrics are actually available to us as epidemiologists, right? So if, for instance, we took a Bayesian approach, we might actually have access to a full probability distribution. We could also potentially just have access to quantile estimates, and there are increasingly epidemiological methods that can take in quantile estimates. And in some cases, if we're just handed an interval width, right, then some folks will think about upweighting or downweighting different of our exposure estimates kind of based on how uncertain we think they are. I also want to briefly provide a different flavor from my recent work. So up until this point, I've been talking about uncertainty estimates for individual air pollution points in space and time, right? But what if instead we're interested in just quantifying uncertainty for a change in air pollution, for instance, attributable to some sort of policy implementation? So in our recent work, we've tried estimating a policy effect and its uncertainty across a large region and time period in regions where we don't necessarily have access to ground level monitoring, and this is why it ties into the remote sensing session. We're able to do this by pairing some of these modern spatiotemporal causal inference methods with existing satellite-derived air quality data sets that themselves don't have uncertainty quantification, but we additionally bring in complementary remotely sensed data products to help kind of flesh out the picture of what's happening. So to make this a little more concrete, the case study or application area we were focusing on was thinking about air quality impacts of plastic waste burning, specifically Indonesia before and after China implemented basically their ban on plastic waste imports after China stopped taking it. A whole bunch of other countries, including Indonesia, received an influx of this plastic waste, a lot of which was openly burned, resulting in increases in air pollution. And part of the way that we're able to kind of estimate this in what we think is a credibly causal way is bringing in additional data sets such as cargo ship loitering density around the coast of the country, which serves as kind of a continuous proxy for where and kind of how much plastic waste imports are entering the country. If you're interested in kind of the mathematical what's happening under the hood, the idea is if we're interested in estimating a causal effect curve here as a function of this proximity to ports, we are using what's called a multiply robust estimator. If you're familiar with a doubly robust from causal inference, this is a very similar idea. Intuition is that we're separately modeling the outcome, PM2.5 air pollution, and also our exposure using flexible machine learning to account for confounding both respect to the time period pre and post intervention, and also to the level of this continuous exposure of how close you are to ports. And of course, as is common across air pollution applications, we have to account for residual spatial and temporal autocorrelation, and we introduce a novel spatial weighted bootstrap to do this. So that's a little bit of the peek behind the scenes of new methods coming out. I'm happy to take any follow-up questions during the lunch or beyond, and I also want to acknowledge my wonderful mentor, Rachel Nethery. Thank you.
Thank you, Ellen. So now we have time for panel questions. We have about 25 minutes, so I invite you to come up and use the microphones on either side of the room to ask questions. I'm going to give it to Christine.
Yeah, and I would invite each of the panelists and Helena as well, if you're online, is just what's one takeaway that you'd want people to know about when you talk about using satellites for health applications, or actually I really liked Ellen's comment on evaluating policy impacts as well as just another application. So yeah, if you had one thing to say, what would you want people to take away?
Start?
You start.
Oh, man. I think what I've seen recently in this space is, well, that I guess I'll just highlight from also this panel was just the importance of working with people who have expertise, right, across whether it's the statistical methods, how these estimates will be used in the later epidemiology, or more on the satellite retrieval side. I think it's too much to ask for anyone to be an expert in all of those things, so I think this panel and this kind of area of cutting-edge research really highlights the need for interdisciplinarity.
Sure. I guess maybe the one thing is, so the big advantage of satellite data, as mentioned, was sort of filling in the gaps where we don't have ground-based measurements. But at the same time, a lot of our sort of satellite-derived surface-level estimates rely on ground-based missions for either direct calibration or evaluating the uncertainties. I didn't mention this in what I talked, but obviously all those uncertainties evaluations that they were doing in this paper were constrained to locations where they had ground-based data to evaluate against. So that is something I think always to keep in the back of your mind and think about the implications of that on the particular case that you're going to be looking at. Are there independent ground-based data you can evaluate against? If not, are there more qualitative uses of the data you can make? I think Ellen gave a great example of in a region without ground-based monitors, she wasn't trying to get at the direct surface concentrations because that's very difficult, but looking at changes and trends and using that information in a smart way to answer your question without having to rely so much on the ground-based information. I don't know if that was very coherent, but yeah, that's what I'll say.
Maybe I see Helena online. Maybe Helena can go next. Answer this question, Helena.
Sure, thanks, Tracy. Yeah, I think one thing that has captured me over the last few weeks is actually the fantastic and captivating images from the Artemis II mission. And just seeing the Earth, our beautiful planet Earth, the one that we know, in this backdrop of just darkness. It really allows us to look at how delicate our Earth is, no matter how you look at Earth from your own disciplinary training. And so that really brings back to forefront really the One Health framework and how many of the international guidelines from different international agencies, which is what your go-to might be, comes across showcasing that we have to do something different, harness new technologies, and that all comes across with Earth observations being part of the toolkit for many people currently, but for me, coming from the health disciplines, it's a new set of tools that I'm constantly learning every day, thanks to colleagues like Tracy and Carl and our HACAS team. And so I think that knowing that Earth observations play one piece of the puzzle is a great opportunity to showcase, great examples like HeyCast, where you bring in many experts to come together from different elements and being able to discuss and identify how we can not only advance the science, but also broaden the science, especially when we think about air quality and health. And some of the revolutionizing missions that we're seeing coming, Tempo currently, Tempo and PACE have been launched and collecting data. We're looking at some other ones, NISAR that has launched, looking at the upcoming from Maya. Just shows the excitement in the community, and we hope that you all get involved.
Thanks, Helena. And maybe just to wrap up this panel, I think, to me, one of the biggest eye-opening lessons learned of the last 10 years working on this topic is how important it is to hear from health experts like all of you in the room, because I think it's tempting to say, like, oh, the data doesn't fit my need. But maybe it doesn't fit your need because nobody's tried to make it fit your need. And what we found with HeyCast is really a lot of the research is propelled by new questions from health professionals and new questions from air quality professionals. And they say, can satellite data do fill in the blank? And sometimes the answer is like, oh yes, you can go to this website or download this data set and it's ready to go. And sometimes the answer is no. There's certain things that satellite data cannot do in their current capabilities. But very often the answer is we don't know. Nobody's ever looked at it that way. And I think that's really what is sparking a lot of new, exciting research. And so I guess I would just, encourage everybody in this room to be part of the conversation to help pose the questions that can really drive this field forward.
Thank you, Tracy.
Hi, Chad Bailey from EPA. I have kind of disorganized thoughts floating around my head, but around three areas. One is we heard a lot different types of satellites. So I guess one question is spatial resolution, and I think it might be a hyper-simplified things that I've seen, like how do you deal with like differences, like how does uncertainty overall map to spatial uncertainty? The other is how do you deal with all the clouds? How many days do you need to measure in order to get, like, how much temporal resolution can you get when you've got, a cloud, cloudy all winter or something like that? And then the last one is how do you deal with nighttime? And especially in terms of understanding, surface PM 2.5.
Great.
So.
Carl, do you want to start that one?
Yeah, maybe I'll work backwards. So kind of using the data set I was talking about as an example, how they dealt with it. So nighttime, that's a great point. So they used the model relationship to estimate, what's the relationship between the AOD at the time the satellites were coming overhead versus the long-term average PM 2.5. So they were using the model to kind of inform that relationship and do that. Now I think that could work better over longer time periods. You get maybe a more robust relationship. That gets to your other question about, how much data do you need? Of course, it depends, but so in that product they were getting down to monthly averages. So that was, for that particular case, you were able to get pretty robust down to a monthly average. I think the trade-off is that you can go to higher time periods, you have more uncertainty, you'd have more missing data. You could do, I think, different people have done either gap filling, so trying to infer what the missing data is to fill in gaps, again, using models to inform what that might be, or just producing data where there are, cloud-free pixels, and just taking, considering the fact that, we will have missing data on these shorter time scales. Depending on what your goal is, you might, need to do different approaches. And then your first question was about spatial resolution. Again, it varies between the instruments. I would say kind of the current aerosol products are on the order of 1 kilometer is sort of the high spatial resolution, and then the trace gas products on the order of 3 to 5 kilometers is sort of the high end of the spatial resolution spectrum there. But again, there's lots of differences between instruments, and there's also opportunities to, again, if you're averaging over long periods of time, especially with these polar orbiting satellites, they're passing over at slightly different locations every day, so the pixels are slightly offset from each other one day to the next. And if you take averages over a long period of time, you bin those pixels at a finer resolution, so you can get some subgrid scale variability just from the fact that the pixels are in slightly different places from one day to the next. So there's been efforts to do that with it's called oversampling basically. So there's this trade-off between spatial and temporal resolution again. I think I'll leave it there.
Do you want to add to the uncertainty? Maybe.
Yep.
Maybe I'll just add one thing, is that beyond the oversampling, which can boost the resolution, there's also a lot of work that's being done to connect satellite data with land use regression techniques to further get to high resolution data products. So if you see satellite-derived products that show individual streets, for example, that's something that is a combination of different data sets together.
I forgot, I wanted to say, so this is the horizontal spatial resolution of the pixel, but you always have to remember that it's looking down through the whole atmosphere. So even if it's getting down to the 1 kilometer resolution at the surface level, if things are smearing out higher in the atmosphere, that's going to limit how much resolution you can get at the surface level, and that's where bringing in covariates and modeling relationships comes in.
Hi, I'm Michael Brower, UBC and IHME. So a couple reflections, a plug, and then a question. Reflection one is I participated in a session at the HEI conference, I think it was 2014. I think Young also was there, about sort of promise of satellite measurements for air quality, and we got absolutely shredded by the audience. And so it's really gratifying to sort of see HEI basically stick with the topic, and also, seeing all the posters that are using this. So I think we, made a lot of progress, and that's really important. In the global health sort of sphere where I work, another, really important advantage is actually these provide a harmonized measurement across boundaries. And it's something that we often put under the rug, but actually networks are not comparable in terms of their siting, in terms of their measurement techniques. And so this has been actually really valuable to actually have a common footing. The plug is the Spartan network. Randall and I started this, I think, 2012. It's the only network that actually has co-located sun photometers and surface measurements, which has absolutely been critical to sort of move this forward. If anybody is interested in actually hosting a site, helping with this, it's always something we're just trying to keep alive. Now, finally, to my question, and directly responding to you, Tracy. So one of our needs, our greatest need right now, from a global perspective, is ozone. Obviously, huge challenges with stratospheric ozone to use remote sensing. But I just wonder, didn't hear any of the speakers even mention that and prospects for, ozone.
Yeah, thanks, Michael, and thanks for all the work you do. I'd say that the greatest potential with ozone, well, first I'll say, speaking kind of retrospectively over the last 10 years, quite often ozone at the surface is in the category of things that satellites just don't do. So I think that because there's so much ozone in the stratosphere, it has been viewed for a long time as something that was just a limitation, and that we didn't want, in part because we don't want to oversell the capabilities of satellite data. We don't want to be, holding out hope for something that may never come. However, maybe it will come, because the new TEMPO instrument is releasing lower troposphere ozone products. And actually, some of the work on the HACAS team right now that was just formed last summer is focused on trying to evaluate those ozone products and think about them in the context of health and air quality applications. Aside from the direct detection of ozone, which would of course be a huge, huge advancement in satellite relevance to public health, I just want to note that part of the ozone story is understanding the sensitivity to precursors, and satellite data do measure NO2, and most NOx is in the form of NO2, and formaldehyde, which is an intermediary product related to VOC reactions, and the ratio of formaldehyde to VOCs has actually become kind of one of the superstars of the way that satellite data can inform ozone reductions, ozone sensitivity, especially in a policy context, even in the absence of a direct ozone detection. But you're absolutely right, and I would say that that's hopefully on the horizon with tempo. Thank you.
We'll go to Inarelli and then
Hi, this is Anarelli Morales from Weld County in Colorado. That was basically the question I was going to ask was about ozone, because like I said on Monday or Sunday, ozone is a huge challenge in Colorado and in the Intermountain West. So I like that you talked about using the precursor data. But this data, I feel like, isn't used as appropriately or at all is considered in our SIP planning. So what do you think it would take? Who do we need to talk to or to pitch or promote the benefits of the satellite data in understanding ozone reduction with respect to SIP planning?
So I love that question. And in fact, the very first use of these precursor detections for ozone regulation was in Colorado by a former, now retired air quality manager at the Colorado Department of Public Health and the Environment. Used it in 2011 specifically because there's this question, ozone is too high. Should we be reducing NOx or should we be reducing VOCs? And perhaps different emitting organizations might view that question differently, And with no data, how do you know? You can trust the models, but the models might be wrong. So actually, we wrote a review of how Pat had used those, and this was near 15 years ago that he was using it. But one of the real problems had been that the data were not in a format that allowed for easy analysis. And so just about 2 years ago, one of my students kind of came to the conclusion that the easiest way to look at ozone precursor data is with Google Earth Engine. And it's not click, click, click quite, but it's much easier than downloading the data into Python. And we have a tutorial on my research group, hollowaygroup.org, specifically about how to calculate ozone sensitivity with Google Earth Engine. And this was reported in EM, the magazine of the Air and Waste Management Association. And after we developed that methodology, it is being used by states. So I know Texas, I know Georgia, probably other states are following this methodology using Google Earth Engine.
Thank you.
Thank you.
Magali Blanco, University of Washington. I have a related but maybe more general question. I'm wondering if you could comment on general efforts to expand some of the pollutants that are characterized with satellite imagery beyond PM 2.5 and potentially at the global scale or maybe at a smaller regional scale. I'm thinking, for example, there are areas where there are efforts to collect really rich spatial information or collect a lot of other pollutants beyond criteria pollutants, and if you know of any efforts of trying to kind of combine those data to.
Well, maybe I'll start this and other people could add. Yeah, absolutely. And if you've ever been on a review panel at NASA, there are all these proposals coming in with saying like, we'd like to use it to detect, fill in the blank. And that might be glyoxal, it might be ammonia. There's a lot of different chemicals that researchers are trying to push the capability of satellite data to detect. And I think there's this question, and isoprene is another one that some work at the University of Minnesota is doing. So I think there's this question of like, can we see this is sort of question one. Is it reliable and how uncertain is it is question two. And then this question like, is this useful for end users like the health community? And I think all of those have to be yes for it to be started to be rolled out as an applied product. And I think, one of the challenges is that we don't want to oversell the satellite data. So if there's just been one study with one chemical compound, maybe that's not the one that we want to like highlight to this audience. And I think that's where the laundry list of all the data products that I showed earlier comes in, that if you have a very specific need, there might be a data product for you, but it may not have been used before, it may not be kind of meant for public consumption because it was done by one researcher in one lab. So I'd say that it is a rapidly evolving area, and maybe I'll shine the spotlight on ammonia emissions, because this is something where ammonia is coming from agricultural activities. it's an important precursor to PM 2.5. It is not something where you have a lot of monitors in the area where it's emitted, and yet satellites can see the breathing of the agricultural systems with seasons and temperature, and so it is being used more and more. So, I'd say this is a rapidly evolving field, and so there's definitely more than these 2 pollutants, but it's just a question of how mature are the applications.
I'm Peter Byerly at the EPA. So Dr. Brower's question got a little bit at what I was going to ask, but I was curious about, if you see in the future, like the next 10, 20 years, and if you've heard about efforts for actual, ground-based or actual ground or tropospheric measurements from satellites, or ozone, but also the other criteria pollutants like PM 2.5, like NO2. I'm just curious if there are efforts being made, ways to sort of isolate, the lowest part of the column density from satellite measurements, just to, instead of relying on other data sources at the ground level, to just do a direct this is our satellite measurement, we got it, or is that sort of a technological impossibility for the future?
Yeah, so I think like Tracy was illustrating in that figure, sort of the AOD PM 2.5 is sort of the most mature along the pipeline. NO2 is maybe a little bit behind that, and then various other things working along with the, I think maybe the new effort now is going to be with this tempo lower atmospheric data product, relating that to actual surface level, and maybe coming up with some estimate products and then having them go through validation, verification, and so forth. So I think there's this pipeline, and something to point out maybe is NASA, sort of maybe the first step in some cases along this pipeline is doing sort of field campaign measurements to target a specific area, fly aircraft at different altitudes, sample the vertical profile, have balloons and so forth, and kind of just collect a lot of data in one place and understand these relationships in a lot more detail to build towards those algorithms. So with ammonia, for example, I know they're planning this field campaign called Farm Flux, which is going to look at vertical profiling of ammonia over feedlots and things like that to work to sort of push things down that pipeline of how do we get at the surface level. And I think there are sort of as Tracy mentioned as well, there are more sort of experimental efforts where maybe it was done as a one-off project to combine ground measurements with satellite data to produce a surface estimate for a specific area. Those sort of get developed and matured over time, and you get to these global data sets which are used and validated more extensively. So I think there's this continuum for many different products. We're moving in that direction, but and yeah, I guess you can come talk to us about specific data products or specific efforts. And maybe a final plug, so there's the Tempo Mission Applications team has their, it's still, I think, called the Tempo Early Adopters Program. It was started before the mission launch, where they brought people on board to get them sort of familiarized with the data and working towards that. So a lot of these missions now will have these kind of early adopters programs before the mission's launched, and then I think they're just still called early adopters. But and that's the opportunity to sort of work more directly with the satellite team to focus on specific products you'd want to see, to sort of get a first look at the products when they come out in prototype versions, and start playing with the data and trying to answer those questions. So maybe that's another opportunity for people to get involved.
Well, and maybe I'll just also make the point that, the satellites are up in space measuring wavelengths. That's really what they're doing. Right. And so one of the great opportunities is to say, how much information can we harvest from those wavelengths? And that's often why you hear the term retrieval. Mm-hmm. I sort of think about the term retrieval like a translation. How do we translate these wavelengths into things that people can actually use? So even when you hear this is satellite data, it usually means it's translated satellite data to interpret a specific metric. And more, actually, some of the translation is being done in the satellites. There's some commercial satellites that have AI on board. Okay. But I don't think that is sort of conceptually, whether the translation is done up in space or whether the translation is done on the ground, I don't think it really makes that much of a difference. I think it's just more, how can we move these wavelengths into products that people can actually implement? Thank you.
Okay. Yeah, thank you.
Hello, Marian Kibujoglu, Brown University. Thank you for the excellent panel. I think this is more of a comment than a comment. I really like that uncertainty is becoming increasingly prevalent in our discussions. We really need that. But I think the comment is that as different groups start estimating uncertainties, we are estimating different things. So there's uncertainty because of AOD, there's uncertainty because of CTM, there's uncertainty because of the statistical model, there's uncertainty as we move away from monitoring stations, or because existing models disagree. And I think all of them are good and great. There's not one better than another, but I think being explicit about what uncertainties we are estimating has implications for how we interpret the uncertainties and how we propagate those in the health models later. And then also we need methods, Ellen, please, for the propagation later. So thank you.
Thank you.
Okay, and then this will be our last question. Go for it. Oh, no, we're good.
I thought we had a lot of time, so I was like, I guess one other question is, air pollution is not the only thing that can be measured or observed from space. And I know for like, there's satellite imagery, photography, and I'm not sure what else. I'm just kind of curious if there's been any branching or connection between air quality and photographs or other stuff, or land use like Landsat, anything like that. What got me started on this, there was an NPR Planet Money podcast that was talking about Planet Labs and how like Wall Street was using it to like measure how full, to measure how full like oil tanks were in, around the world. And I'm like, well, that could be really interesting. So I'm just kind of curious if there's any efforts underway to sort of bring all of that kind of different space type stuff together.
So maybe I'll comment, and I think Alina would be a great person to comment on these broader applications. And Ellen, yes, I think. But to say that absolutely, I think there's the issue of what is happening in the commercial sector as well as public applications. And within NASA, they have an Earth Action Program where health and air quality is just one of a few different divisions. And I love that you mentioned Planet Lab and the oil tanks. Actually, one of the projects that I'm working on outside of health is working with the Energy and Infrastructure Group at NASA to better characterize and broaden the applications to energy decision making. So I think, and that idea of financial companies using information on large-scale observations to understand market trends is a great example. So, I would just say that, what the discussions that we're having here in the health community are being mirrored in both startup companies and public sector application areas in many other fields.
And then I will also add, so because of time, I didn't articulate all of this, but in our plastic waste burning study, we actually tied in a lot of different remotely sensed data products that were not just air quality. So the cargo ship loitering was one. That's actually, it's cargo ship signals are how they derive the density. And actually, we just use when they're loitering, but they track them, the ships wherever they're going over the ocean. So that was one data product we tied in. And the other one that really enabled the plastic waste burning study was there's an organization, Global Plastic Watch, that had identified basically locations of large open waste aggregations. So applied machine learning to imagery to identify, where are these large open dump sites. And we basically, also used that to identify, hey, the locations that we're actually looking at air pollution to kind of triangulate, the effect due to open burning of this plastic waste. And so I think this has interesting kind of ties in with the accountability session that happened on Sunday, where when I'm saying triangulation, I'm meaning kind of within the same study, but if we're bringing in data sets of different types with kind of these rigorous, say, causal inference methods or other methods where we're making, very clear assumptions, basically that can help us to have a greater confidence that we're seeing some sort of, say, effect attributable to a policy, even when each individual data source itself might be a little bit noisier.
Thank you. Helena, did you have any other comments to that?
Yeah, Just echoing off of, thanks to both of you. Another thing to expand, looking as Tracy had alluded to, is the Commercial Satellite Data Acquisition Program, or CSDA. There's a lot of push on that, especially as how it's going to meet the NASA's Earth Science to Action strategy to help decision makers use Earth observation data faster and help to kind of accelerate and advance the impact. So those are some great opportunities, especially with some of the launches that have occurred over the last few years when we think about PACE, Tempo, NISAR, and others, and some of them have those early adopter programs. So a great opportunity to learn a little bit more, especially about some of these commercial satellite data opportunities.
Thank you. Yeah, and that gets to the emission estimations, and there's so much potential out there. It's so exciting. I'm just going to really thank the panelists today for their comments. I think this observational data set and the opportunities here are just really limitless, and there's so much more potential. I mean, I'm really excited just to hear what's happened in the last 10, 15 years, and seeing it myself has been extraordinary. I think it's critical that we recognize the limitations, and that's been brought up a lot here, and I think just understanding that, and then the need for this collaboration and cross-disciplinary interactions. It's really to have this advancements in health and air quality assessments, understanding policy implications, identifying source apportionment, bringing people together from different fields in this space is really key, and we heard about some really excellent examples today. So again, I'm going to invite Allison Patton to come up and talk about our next HEI opportunities. But in the meantime, let's thank our panelists as Allison comes up. Big green button.
The big green button. Okay. Thank you all for such an excellent discussion and all the questions. This is a topic that's really exciting because of all these new data sets and all these new connections across fields. I'm here to tell you about HEI's newest studies in this area. So first, we've heard, I won't go into details on the background because you've basically heard it. We had that workshop that Heather talked about a few years ago. Coming out of that workshop, we discussed research needs to make data from satellites more useful for health studies. And so there was an RFA that came out of that workshop. And this RFA had several specific objectives. Its overall goal was to develop a resource of satellite data with uncertainties that could be used effectively in health studies. And also with that data set to really understand and communicate the limitations and the strengths for interpretation in exposure and epidemiological and health assessment research. The two main objectives were first to develop that resource, including with code and instructions and tutorials to make sure that the data could be used effectively. And the second was to evaluate the regional and local accuracy of the new approaches and data and tools. And the focus would be on air quality in the United States, especially in rural areas that might not have as much data available. And so we put out this RFA, and we received 50 preliminary applications. It was a very impressive set of applications. The research committee reviewed those preliminary applications for responsiveness to the RFA and some other factors, and invited a subset of full applications. Those applications were reviewed by an external panel of experts in satellite data, in uncertainty assessment, and in exposure and health studies for air quality. And so this is HEI's standard process, and we were very impressed by many of the applications. The board of directors approved the studies, and right now we're just at the cusp of study negotiation and starting. So I'm really happy that I'm able to tell you the two new studies. The first is from Dr. Marianthi Kimertzoglu, and she's at Brown University and will be preparing NO2 products using Tripomi and Tempo data. The second study is by Wangsheng Li at Emory, and his team will be producing data for NO2 and ozone and PM2.5 based on Tripomi and VIIRS data. And I think they're both here. I saw Marianthi asked a question. She presented a poster on Sunday, and Wangsheng will be presenting a poster in the next session. So you can ask them about what they plan to do, or you can catch me at any time. So we expect that these studies will have useful outcomes. First, providing resources for use of satellite data in health studies over the contiguous United States at 1 kilometer resolution. They'll provide data, code, examples, tutorials, things trying to make these data more accessible to people who might not have otherwise used them. They'll be using Bayesian approaches to assess uncertainty, accuracy, precision, and bias. And they'll also importantly be engaging with multiple sectors. So as you heard, that engagement's really important. They'll be working with HACAST and RSET, trying to understand the data better, and also state and federal agencies and research institutions to talk about the end users and how to make the data most useful for end users. And so I'm really glad that I've been able to present these new studies to you. Also, thank you to the panel. Are you announcing this, Dan, or? Okay, and Dan has an announcement about our special guest.
Oh, and also, I just want to thank Allison for all of her work to organize this panel, too. So.